We're now to our final component that we need for weather and climate. We've got temperature, we've got winds, but now we need rain. We need precipitation to take place, whether it's rainfall, whether it's condensation from fog, whether it's snow, ice. This is water. And so we've got to understand the properties of water and how it behaves. And fortunately, it behaves relatively consistently. So we've got our three states of water. We've got water as a solid, which of course would be ice, glaciers, snow. Also, we've got water in its gaseous form. Those are the individual water molecules that are floating in the air. And then liquid water, which of course would be rivers, oceans. But I'll come back to this more later, but it's also the clouds that you see. Clouds are liquid water. They're very, very tiny water droplets, billions of tiny water droplets. But water in its gaseous state, you cannot see. You cannot see individual molecules, but you can see liquid water. There's just a lot of little droplets that make up the clouds in the sky. Now the diagram here is what it's trying to show is that the water, as it changes states, it goes from when it's a solid, it creates a matrix. When it's liquid, they're bonded together. And then when they're the gaseous form, they're floating around. But in order to get each one of these states to change, there involves energy. So you're either absorbing energy or releasing energy when you're going through these different states in order to get those bonds between the water molecules to either come together or to break apart. So evaporation, what's happening here, we're going from a liquid to a gas. And in doing so, the individual water molecules, they absorb some energy because it takes energy to get those molecules to break apart, and you can't destroy energy. So once you use the energy to break apart the bond between the molecules, those molecules take that energy with them, and they store that energy in the individual molecules that they'll release later. And so latent heat is that stored energy in evaporation. So if you're removing energy in the process, so it took energy to get those water molecules to break away, and then you take that energy away, it's a cooling process. And so evaporation is a cooling process. Later, when we talk about condensation, it's the opposite of this. It's a heating process where evaporation is a cooling process. And that stored energy is referred to as latent heat. So one of the fun things about water is that it behaves very, very consistently. If we know how much moisture is already in the air and what the temperature is of the air, we can calculate how fast evaporation will take place. We can calculate how much water will be lost in the process, and then changing either one of the variables, the amount of humidity or the temperature, we can affect how fast something evaporates. I'll take the extremes. A very hot temperature and low humidity in a desert has a very high rate of evaporation. If it's relatively cold out, say it's 40 degrees, and there's already a lot of moisture in the air, the evaporation rate will be very, very slow. And so the big difference would be, you could do it at home if you're bored, 2 glasses of water, identical amount of water in them. You put one in the refrigerator and you put one outside. Come back and the next day or two or later, and you'll notice that the one outside, the amount of water in the glass is decreasing faster than the amount of water in the refrigerator. Now we measure humidity, the amount of moisture in the air. There's a few ways to do it. We're just going to stick with the basic concepts of absolute humidity and relative humidity. Absolute humidity is how much water is in the air. It's literally a measurement of the water molecules in the air. It's independent of temperature, so you can have consistent absolute humidity even though temperature changes. And why temperature change becomes important, because that's your relative humidity. Because warmer air, the air molecules are moving around furiously, and those air molecules can keep those water molecules in suspension. So warmer air, faster moving molecules, they can hold more water. And when the air cools, the air molecules move slower. They can't hold as much water molecules in suspension, and so they don't have as much capacity to hold water molecules. So the relative humidity measures that. What's the air's capacity to hold the moisture? If it's hot, that's great capacity. So in the diagram you're seeing, the absolute humidity does not change. The amount of the total amount of water in the air isn't changing, but the larger the circle, the greater the capacity. The larger the circle, the warmer the air. And so when it's warm out in the afternoon, it can hold a lot of moisture. So we're only at 20% humidity. As the morning starts, I just realized I've been doing this lecture for a gazillion years, and the times on this are really strange. Anyway, when it's cooler out, the capacity is reduced. We didn't change the amount of water vapor, but the capacity is reduced. Now we're at 50% capacity. We're at 50% humidity. At some point, we may cool enough where the capacity of the air can no longer hold that water in suspension, and so it will have to be, something will have to change in that dynamic if it's at 100% capacity. So we see those effects of air temperature on relative humidity, not on absolute humidity. Now, if this gets even cooler, we're going to have to get rid of some of those water molecules. They're going to have to go from a molecule back to liquid water, and that will be the condensation process. So this was another diagram that I'd come across where if you're looking at the warmer air having a greater capacity, that's the bigger glass. And so this would be the same temperature air. And if this one has less absolute humidity than this one does, this one would only be at 50% humidity. But the same temperature, if there's more absolute humidity in the air, then they're at 75% capacity. So if we take this warmer air and cool it off, then it's a smaller capacity, can't hold as much water, and so it's at 67% humidity. At some point, if we keep cooling it off, the capacity decreases, the size of the glass decreases, and then we finally reach 100% humidity. Now, unfortunately, there are 5 different ways to describe air that has reached 100% humidity. And it's all in context of what you're referring to. And you'll notice I've listed 4. We'll get to lifting condensation level later. That's the 5th way to describe air that's become saturated. So saturation is implying that it's reached 100% humidity. Saturation and 100% humidity are almost interchangeable. Condensation is when you're referring to the process that ends up taking place. Condensation occurs when air is at 100% humidity. The water molecules go from individual vapor to a liquid or to a liquid form. So that's condensation. If you're talking about the temperature at which this happens, remember, the cooler the air, it's going to cool to the point at which it reaches 100% humidity. If you're talking about the temperature, that's the dew point. So all of them are referring to the same thing, but it's the context of, are we talking about the temperature, what's happening to the air, is it saturated, or are we talking about the process of condensation taking place? So condensation releases latent heat. So if we had evaporation was a cooling process, condensation is a slight warming process. And how do you get to 100% humidity? I've only talked about cooling air because that's the more common method. We'll see why that in nature, when we get our rainfall, it occurs with cooling air. But you can also add moisture to the air. Out over the open ocean, there's evaporation taking place. If you're in your bathroom and you're adding the moisture with a shower, there's a lot of water vapor coming off the shower, the warm water, and it'll condense onto the mirror. But in the sky, when that air cools to its dew point temperature, it doesn't become a block of solid water in the sky. What happens is it condenses onto dust and fine-grained particles in the sky. And so when it condenses on those small particles, it's little tiny water droplets. So the diagram on the lower right is showing a raindrop, which is huge, but, well, relative to a water droplet, the water droplets are so small that slight up breezes and movement of the air will keep them in suspension. And so as long as we've got a little bit of an updraft movement of the air, those small water droplets will remain in suspension. It's kind of like the mist setting on a water bottle, actually slightly smaller than that. So that's when you mist a sprayer and you see that water droplets kind of go out and they'll hang there in suspension, then they'll slowly sink down. That's because they're very, very small droplets of water. Now in the morning, you'll go out and see sometimes if the absolute humidity was high enough and the outside air temperature was low enough that air may have become saturated and it needs to condense onto something. And so ground, grass, often they lose a lot of heat relatively quickly, and so they become very cold, and so it will condense onto that blade of grass. If you had a glass of water with ice in it, and you see the water droplets on the outside, we all know that the water didn't leak through the glass. The air that was in contact with that glass got so cold, it reached its dew point temperature, and it condensed onto the glass. Or the case with my car in the morning, when I've got the condensation on the windshield and glass and metal, the glass and metal don't hold heat very well, so they cool off quickly. And so even though the ground itself around it doesn't have dew on it, my car got colder than the ground. And so it released so much heat, the air in contact with the car reached its dew point temperature, and it had to get rid of the water molecules, and it got rid of them onto my car. Well, you'll see my real car later. So there's an inverse relationship between humidity and temperature. The greater the temperature, the lower the relative humidity. The lower the temperature, the greater the relative humidity. So it drives me nuts when newscasters in the afternoon will say, we're going to have increasing humidity overnight tonight. And I'm like, well, duh. It's going to get colder tonight, so of course humidity is going to increase. And guess what? Tomorrow when it gets warmer, humidity is going to decrease. Now, this is all things being equal. This is, we don't have a new air mass moving into the environment that's humid, but this is just tonight, everybody, it's going to get more humid. Well, how do we cool the air? Now, before we go on, I have to apologize. This is one of the more complicated slides of the entire semester, and I'm going to go over it different ways. I'm going to show different examples of what's going on. So, fortunately, since this is video, you can back up and look at it and go forward to the different aspects of this. But the important concept is that one of the ways we can get that air to cool, the way we get that air to reach 100% humidity, is to have the air get lifted up. And we'll talk about the different ways that air can get lifted. So we have to understand that process, that lifting is a cooling mechanism. And so remember, water behaves very consistently. So as it rises, it cools at a consistent rate. And as it descends, it warms at a consistent rate. And this is always going to happen. Rising air cools, sinking air warms. So the rate at which it cools or warms is either the dry rate or the moist adiabatic rate. The dry would be if you're below 100% humidity. It's going to cool at a certain rate. The moist would be if that air is at 100% humidity, it will cool at a different rate. When it reaches 100% humidity, it doesn't cool as quickly. And what happens is that the cooling of the air as it rises is affected by decreasing air pressure. So the higher up you go, there's less air pressure. Less air pressure, less molecules being pushed into each other, and it cools it off. It's a similar process to the lapse rate we talked about before, but this is moving air. Lapse rate was static air, this is moving air. So the lower air pressure leads to lower temperatures. Well, that's consistent at 5.5 degrees per 1,000 feet. But once condensation takes place, because the air is 100% humidity, it's been cooling off as it's rising up. At some point, as it cooled, it's going to reach its dew point temperature, and when that happens, condensation takes place. Well, condensation is a heating process. So I have two different processes happening at the same time. I have the cooling from rising, and I have the warming from condensation. The cooling from rising is more than the warming from condensation, so it doesn't quite cool as fast. So instead of at 5.5 degrees per 1,000 feet, the condensation takes up about 2.2 degrees of that, and so it only cools at 3.3 degrees per 1,000 feet. So it's still cooling as it goes up, it's just not cooling quite as quickly. Well, what about sinking air? Well, warm air, if air sinks, it warms. So warmer air has greater capacity to hold water. So as soon as you start to warm the air, it drops below 100% humidity. You can't have warming air stay at 100% humidity because just warmer air can hold more water, and so that messes up the equation for relative humidity. So warming air always is below 100% humidity. So if there's no condensation taking place, because you're not at 100% humidity, it will warm at the same rate it cooled without condensation taking place, because the pressure is still changing. As you go down, there's increasing air pressure, so it goes up at 5.5 degrees per 1,000 feet. So you'll cool at one of two rates, and then you'll descend at the same rate. Let me go through this a few ways. So again, rising air always cools, sinking air warms. And when rising air cools, humidity, relative humidity, increases. When sinking air warms, the relative humidity decreases. Now here's that fifth little variable, fifth term for air that's reached 100% humidity. This is the context of, instead of asking at what temperature did it reach its dew point, this is asking what elevation will it reach its dew point temperature. And they're connected with each other. There's a chart you can look up. If the air is going to cool by 5.5 degrees, it's got this much absolute humidity in it. When will it reach its dew point temperature? There's a similar chart where the air is at X thousand feet. This is the absolute humidity. You can look it up in a chart and it'll tell you how many thousand feet it needs to go up before it reaches its dew point temperature and before condensation takes place. So it's a similar concept, just different math. And so this is an elevation at which air reaches 100% humidity. So the flat bottom you see of clouds, that's telling you that above that elevation, the temperature has decreased so much that air is condensing. Below that, the air is not condensing. It hasn't reached its lifting condensation level yet. It hasn't reached its dew point temperature. So it's below 100% humidity. All right, this is one of my favorite equations because I'm weird. Orographic lifting is one of the ways you can get air to rise, and it's the easiest way to demonstrate the adiabatic cooling and warming rates, and also the difference between the dry rate and the moist rate. And I'll walk this through you and you'll get a few ideas. And so the diagram in the upper right, which was supposed to repeat and it doesn't appear to be right now, the air is rising. It reached its dew point temperature at the lifting condensation level, but the air keeps going. The air is going to go up and over the mountain and down the other side. So the air, somebody went out and measured the air at 80 degrees, but they also measured how much moisture was in the air. And in doing so, they calculated the elevation, they calculated the lifting condensation level for that air. And they told us it was at 3,000 feet. Somebody can't just go out and measure the air temperature and just say this is what the lifting condensation level is. You have to have two parts to that equation. You have to know the air temperature and how much moisture is in the air, and then you can look it up in a table. For those of you in the lab, you will do something similar to this. I'm not going to make my lecture students do it because it's complicated. So if it's 80 degrees, it's going to go up 1,000 feet. It's going to be cooling. It's going up. So we drop it by 5.5 degrees. Goes up another 1,000 feet. It's cooling. Drop it by 5.5 degrees. Goes up another 1,000 feet. Drop it by 5.5. But now that we reach 63.5, the dew point temperature for that air, condensation takes place. See my little cloud? That's the condensation. So now it's a heating process a little bit. So it kind of reduces the cooling. So now we use the saturated rate, which is only 3.3 degrees per 1,000 feet. So we drop it by 3.3 and keep going up and drop it by 3.3. So it still cooled on the way up. It didn't cool quite as fast that last little bit. So when the condensation was taking place, we're literally taking water out of the air and making it into a cloud. So the absolute humidity is decreasing as well. So even though it's at 100% humidity, we're taking water out of the air. So there's less water in the air up here than there was in the air down here. When I say less water in the air, I mean less individual water vapor molecules in the air. All right, so now we're going to go down the other side. And when you descend, remember it's warming, so descending is warming, Warmer air has greater capacity to hold moisture. We're no longer at 100%. No more condensation. So we warm at the dry rate, adding 5.5 all the way down. Awesome. We can calculate temperatures all the way through. We know the amount of moisture in the air just because we took one test over here. We can tell you how much moisture is in the air all the way around. We can tell you the relative humidity over here. We know the relative humidity here is 100%. But look at something else unusual. We started at 80 degrees and now I'm at 84 degrees. Because we warmed all the way down at 5.5, but we didn't cool 5.5 all the way up. Condensation messed it up. No condensation over here. And so it just warms because of increase in pressure all the way to 84.4. Also, the amount of moisture in the air here is less than the amount of moisture in the air here because we took moisture out of the air to make the cloud. So the condensation took moisture out of the air. And so not only is it warmer, but it's drier. We've just created a rain shadow. Lifting condensation level, you can see the flat bottom of the clouds. So the concept of a rain shadow, the only reason I put windward, leeward is that people often forget what those terms mean. Windward is the side that gets the wind. Leeward is the other side. But the side that gets the wind, that's going to be the green side of the mountains. The other side is going to be dry. And I'll give you some examples of that. Even locally, most of our wind systems come out of the west. And so our local Santa Ana Mountains right here, we're on the wet side, so they tend to be green. If you're on the other side of it in Corona or Lake Elsinore, it's significantly drier because they're a rain shadow of our local mountains. So you can see other rain shadows here. Here's the Rockies up through here. Creates a rain shadow in this part of the United States. Sierra Nevadas creates a rain shadow in Nevada. The Coast Ranges and the Cascade Ranges create a rain shadow in this portion of Oregon and Washington. I mean, people often think Oregon's nice and green. Well, yeah, the western part is, and same thing with Washington, but certainly not the eastern part. Colorado is a night and day difference between being in western Colorado, green, rocky mountains, beautiful, and the brown flat plains of eastern Colorado. So this is an unusual perspective. You're looking south down the Sierra Nevadas. So Nevada would be over here. California would be over here. And so somewhere in here is a national park. I don't think it shows up in this particular photo. And so the air comes out of the west, drops its snow as it cools over the Sierras, and then descends the other side into the Owens Valley. So if you've ever driven to Mammoth and you went up the Owens Valley, it's brown and stark and not very attractive. That's because it's the rain shadow. It's warmer and drier on this side than when the air started on the California side. Even Hawaii has a rain shadow effect. The trade winds come out of the northeast. The California gets the westerlies. Hawaii gets the trade winds. And so the wind comes from that direction. And so the northeast side of the islands are always going to be the wet side of the islands. If you really, really want sunshine in Hawaii, the sunniest place is the Kohala Coast in through here because it's got two massive mountains, Mauna Kea and Mauna Loa, over 13,000 feet that create a pretty significant rain shadow. But it's not lush green vegetation. That's what you get on the windward side of the islands. But you get rain, but you get the green vegetation. The leeward side, this is tropical savanna, very dry. Most of the resorts on this side have to irrigate all their tropical plants just because it's too dry. Look, lifting condensation level in the background too. So we'll come back to clouds and methods of lifting air in our next episode.